Welcome, welcome, party people. Alrighty, so today we are going to do chapter 3 in the Cutnell book. Which is motion and two dimension. So we're doing kinematics in 2 dimensions today for chapter 3. Now, before we go ahead and start, I would like to refresh on some stuff that we talked about last time. So we talked about vectors. And let's say if you have a vector that's going in, let's say this is our vector R, that is a resultant of, actually, let me get different colors on that. This is going to be a resultant of the X and the Y vector. So there's going to be R in the X, and there's going to be your R vector or R vector on the Y. Actually, there's going to be your X, and there's going to be your Y. And this will be your angle theta. And basically, so this is going to be your hypotenuse. Okay. And we talked about if we have the angle sine theta, which is going to be your opposite over hypotenuse, which is in this case is going to be your y over hypotenuse, which is in this case would be your ry over r. That's why your r vector and the y vector is going to equal to r sine theta. Same thing for cosine theta, which is your adjacent over hypotenuse, which is going to be your x-axis over hypotenuse. In this case, it'd be your r over x over r. That's why your r in the x direction vector is going to equal to r cosine theta. Which results in tan theta, which is your sine theta over your cosine theta, which is going to be your y over hypotenuse divided by x over hypotenuse. Again, your hypotenuse cancel out. So that means your tan theta is going to be your y over your h. We also talked about displacement in 1D. So let's say if you have a displacement, let's say you have an object that moves at 5 meters, and then it goes in and moves at 3 meters, your resultant should be your 5 plus 3, which is 8 meters. Now, let's talk about motion in 2 dimensions. So supposedly I have an object. This object, let's say I got a road going in a circle, and I got a car. So let's say this is my car that's going in, and that's your initial position over here, and it's in your final. Here's my car over there. It's in the final position. I'm going in around about, going this side. And so if we actually look at the displacement for this object, let's say I got my axis is right over here, and you go in from one displacement, and again we do hit the tail on the first one. Hit the tail. So let's say this is your initial precision. This is your final. Actually, I'm going this way. So here's your initial position, which is going to be your R naught, followed by your final R. We'll just say RF or R for the radius that we're going to starting in. That means that this one that goes over here, that's your delta, which is delta R. And so we define R as your final position. R naught as your initial position, and delta R, which is your displacement, which is going to be your R minus R naught. And they're vectors, so we need to have your arrows on top of them. Well, if we have a vehicle that's going with a displacement R, that means we have that vehicle has an average velocity, V. So you go V average, which is going to be your average distance divided by your average time. Now we define the velocity itself as distance or displacement over time. So in this case, your average velocity is going to equal to our displacement that we just have, which is R minus R naught, final minus initial, divided by time final minus time initial, where let me go ahead, T is going to equal final time, and T naught is initial time. Change of R over your change of time. Now notice we do not have our little arrow on top of the time because time is a scalar, not a vector. And we also define the acceleration, let's say the average acceleration, as your change in velocity. Let me go ahead. Your acceleration is your velocity divided by your time. And V, that's your velocity, which is this fellow over here. And T, that's your time. So average velocity is defined as your final velocity. And let me go ahead and write this down. V is final velocity. And V naught is going to be your initial velocity. So we define the acceleration as your final velocity minus your initial velocity. And again, these are vectors divided by the time is taken, which is T minus T naught. So this is going to equal to your delta V over your delta T. We also, in the last video, we defined the equation of kinematics. Equations of kinematics, where we had your final velocity equals your initial velocity, over your naught, plus A of t. Your distance x is going to equal 1/2 V naught plus V. Maybe I'm going to stick with V as V final times t. We had your V final square is going to equal your V naught square plus 2A x, and x is going to equal V naught t plus 1/2 AT squared. And we defined x as the distance, and we defined A as the acceleration, T as your time, and V as velocity. Now, and that's in 1D. Now, let's say you have a spacecraft. Let's say you got, I don't know, this is a spacecraft over here. And here there's a little cockpit going in. Let me just go ahead. This a better looking plane. Let's say we got a little plane over here. Let's say we have a little spacecraft going in. The spacecraft is actually moving at a direction of v in the x direction. That's going to end up, let's say this is v naught in the x direction, that's going to end up being right over here. Get our little plane again. Going in at v final at the x direction. Now, one thing we want to know when we talk about 2D, that we have a horizontal for 2Ds. We are dealing with a horizontal direction which is your x direction, and a vertical direction, which is going to be your y direction. Now, your horizontal direction is, well, it happens independently of the vertical direction. So going back to our plane example, this one, we got a plane. This plane has the ability to go on sideways, and let's say it has some jets only on the bottom that has the ability to take a velocity at a y direction. So you get a v final v initial of y, v final of y. So basically, we're talking about two things. We're talking about your x horizontal and your vertical, which is going to be your y. And because we mentioned that they have it independently, that means each one of them has a vertical one. So for your x-axis, your kinetic equations will be your final velocity. Let me go ahead and get a different color. Actually, let me go ahead and get on here. X and y. Which is going to be vertical. Horizontal. So our first piece of equation was v equals v naught plus AFT. That means your final velocity in the x direction is going to equal your initial velocity in the x direction plus AFT. And your final velocity in the y direction is going to equal final velocity, your initial velocity in the y direction plus A of t. Our second equation was x equals 1/2 v naught plus initial plus final velocity times t. So for the x-axis, the direction in the x, let me get a green for that one. is going to equal 1/2 V initial X plus V final in the X direction times T. The same thing. For the Y axis, the distance in the Y direction is going to equal to 1/2 the velocity, initial velocity in the Y direction plus the final velocity in the Y direction times T. The third equation that we had, which was in the one dimension, V squared, V final square equals V initial square plus 2AX. So Vx squared, again, in the X direction, V final in the X direction square is going to equal the initial X squared plus 2 times the acceleration in the X direction times the distance X. For the Y vertical, your Y is going to, your final velocity in the Y direction is going to equal the initial velocity in the Y direction square plus 2, the acceleration in the Y times the Y distance in the Y direction. Finally, the last equation that we have, which is X equals your initial speed, initial velocity times T plus 1/2 AT squared. That means your X equals your V naught X times T plus 1/2 A acceleration in the X direction times T squared. If you look at the Y, same thing, but it'd be in the Y direction is going to equal V naught Y plus 1 times T plus 1/2 AY times T squared. And that will be your kinematic equations for that 2 dimension. And again, for 2D, we are dealing with horizontal and vertical X. That means the horizontal direction happens independently of the vertical direction. That means the X part of the motion happens exactly as it would have if the Y part did not happen. So let's do an example, shall we? Actually, we have an example over here that we can actually go ahead and do. So you got next direction, small spacecraft has initial velocity component of 22 meters per second, acceleration of 24 meters per second. In the Y direction, the analog quantities are 14 meters per second and 12 meters per second square at a time of 7 seconds. Find the distance X and the vertical velocity in the X direction. You also want to find the distance Y and the horizontal velocity in the Y direction and the final velocity of the spacecraft. All right. So again, going with my Dr. Malek's 4 rules. And if you know anything about the marble, that's going to be your Fantastic Four. So this is my Fantastic Four rules, which is number 1, write down the info. Number 2, something is going to equal your double question mark. Number 3, write down the equation. And number 4, like plug and play, this is going to be plug and solve. So so these are the 4 rules that we're going to be using every time we're going to be working on a problem. So going on this problem over here, which is going to be example 1. The first piece of information that we have in the x direction, and let's say we got the x direction and the y direction for the information. For the x direction, we have an initial velocity component of 22 meters per second. So that means our v naught of x is going to equal 22 meters per second, with an acceleration in the x direction at 24 meters per second. So a of x is going to equal 24 meters per second squared. We also have in the y direction, that's going to be the initial velocity in the y direction, which is 14 meters per second, with an acceleration y of 12 meters per second squared. With our time being 7 seconds for both. So that satisfies our first rule, which is write down the info. Now, what are we looking for? Something equals question mark. We are looking for your x and v of x. So we're looking for our x and our final velocity in the x direction. We are also looking for, same thing, your y and your velocity in the y direction. That's for part A. For part B, we are also looking for the final velocity of the spacecraft at 7 seconds. So we're looking basically for the final velocity overall component. So, which is your overall V. All right. Well, let's start in the first one. All right. Let me get this. So in the first one, we're looking for your x. What we do not have is your final velocity. So looking at our equations, we're looking for the x, but we do not have the final velocity. That means this has final velocity. We cannot use this. This has final velocity. We can use this. This one does not have final velocity. This equation over here. So what we can say is your x and here's your y components to solve. So for this one, your x is going to equal your initial velocity in the x direction times t plus 1/2 at squared. Same thing for the y. Your y is going to equal v naught y times t plus 1/2 at squared. Solving this from our information, so what you get, 22 times 7 plus 1/2 times 24 times 7 squared, which if we multiply, let me go ahead and plug in my calculator. You got 740 meters. Actually, let me get a different color for that one. Okay, applying the same thing for the y, which is going to be initial velocity in the y times t plus 1/2 at squared, which is going to equal your 22 times 7. Not 22, I'm sorry. The velocity for the y is 14. So it'd be 14 times 7 plus 1/2 times 12 times 7 square. Plug in this into my calculator. So I got a direction magnitude of 390 meters in the y direction, and we have in the x 740 meters in the x direction. Now, that's for the first one. So we found out these two. All right, well, let's find out the next one. Your velocity in the x direction, your velocity in the y, your final velocity in the y direction. Let me go ahead. So your velocity in the x direction, your final velocity in the x direction is going to be the following. Now, we are not going to be able to use any of them. So we're going to be using the final velocity in the x direction equals v initial velocity plus aft, which is in our case is going to equal initial velocity x plus aft, which is going to equal to 22 plus your 24 times 7. So there's going to be 190 meters per second. Same thing, solving for the velocity in the y direction is going to be initial velocity in the y plus aft, which is going to equal to your 14 meters per second plus 12 times 7, which is going to be 98 meters per second v of y. This is your final velocity in the x, which means that we have a resultant of v of x, which is 190 meters per second. You got your v of y, which is going to be your 98 meters per second, which is the resultant for your v with an angle theta. Now, your final velocity, and then we need to find that at the v direction, you use the Pythagorean theorem, is going to equal to your square root of your v of x squared plus v of y squared. Which is your magnitude of 198 meters squared plus 98 meters squared, which you should get 210 meters per second. Now, to find the angle that we're actually going at, your angle, which is going to equal to your inverse tangent of y over x, which is in this case your 98 of y over x. Or in this case, your v of y over v of x, which is going to be your inverse tangent of 98 over 190, and you should get 27 degrees. So your theta is 27 degrees. That means our plane was going at 27 degrees with a magnitude of 210 meters per second. Now, awesome. Now, under the influence of gravity alone, the object near the Earth surface will accelerate downwards at 9.8 meters per second squared. Now, or vertically, your acceleration is going to equal minus 9.8 meters per second squared, which is going to be your acceleration in the y direction, which is going to be 9.8 meters per second squared. Where if it's going down minus 9.8 meters per second squared, that means your a of x is going to equal 0. Again, your x and the y are independent from each other. So let's do an example, shall we? The airplane is moving horizontally with a constant velocity of 150 meters per second and an altitude of 1,050 meters. This plane gets a package, determine the time required for the care package to hit the ground. Now, you have a projectile motion that's actually going downward. So you have a vehicle, let's say this is your plane. and it has a care package. This care package that's being dropped that has a vertical x velocity of 115 meters per second. Now, your initial velocity in the y direction is going to equal 0 meters per second. And the reason for that is because it's going in the x-axis, the y vertical axis did not interfere with the x-axis, so it's actually starting from the initial, which is 0. Going in our 4 rules. So your first piece of information, again, your v of x, which is 115 meters per second, and your altitude of 1,050. Now your altitude is, so here's your ground over here, and this is going to be 1,050 meters. That means this is going to be in your y direction. So your y is going to be 1,050 meters. Now your package is actually going downwards. That means you have an acceleration. Actually, let me go there on this one. This package is going downwards. That means it has an acceleration in the y direction, which is going to be minus 9.8 meters per second squared. So a of y equals minus 9.8 meters per second squared. And it's asking for the time required for the care package to hit the ground. So we're looking for our time, t, using our kinematic equation, the one that we're going to be using. So the only one we don't have is the final velocity for y. So we cannot use this one that has a final velocity. We cannot use this one. We cannot use this one. So that means we have to use this one. Again, these are the final velocity, v of y, and this is the initial velocity. So the equation that we said we're going to be using is your y equals your v naught y t plus 1/2 acceleration in the y direction times t squared. Which means, solving for this one, again, we call the v initial for the y direction as 0. So this little fella goes to 0. That means your y is going to equal to your 1/2 a final in the y direction times t squared. Acceleration in the y direction times t squared, which means solving for the t is going to equal the square root of 2 times y divided by the acceleration in the y direction. That means your t is going to equal the square root of 2 times now your y is 1,050. That means you're going minus 1,050 in the negative y divided by minus 9.8 meters per second squared. Or you can say it's 1,050 divided by 9.8. The negatives will cancel out anyway, and you should get 14.6 seconds. So the time for the package to drop the floor is 14.6 seconds. All right. Now find the final velocity the final vertical velocity. Which is your final velocity in the y direction. Now, knowing this, we just plug it in one of the kinetic equations. So we just use the final velocity in the y direction equals your initial velocity in the y plus a of t, which is in this case is going to equal, we said this one's going to go to 0 anyway. So it's going to be your minus 9.8 times your time that we just found, which is 14.6 seconds. So that means our final velocity in the y direction is going to equal to minus 143 meters per second, which means that the final, again, your final velocity, your resultant velocity, which is going to be your x velocity square plus your y velocity square, is going to equal to all right. So our v of y is 143, so this will be 143 squared. V of x, we can calculate v of x final as v initial of x plus a in the x times t. Again, because we are going down, that means our a of x is going to equal to 0, which means that our final velocity in the x direction is going to equal to our initial velocity in the x direction, which is going to equal to, from the equation, 115 meters per second. So this is going to be 115 squared. So that's going to equal to we got is 100. So your final overall velocity is going to be 183.5 meters per second. All right, let's do one more example, shall we? Now, for this example, though, the next example that we have in, you get a place kicker that kicks the football at the angle of 40 degrees, and initial speed of ball of is 22 meters per second, ignoring air resistance, determine the maximum height of the ball. So you get a kicker that kicks, this is going to be example 6. You get a kicker that kicked the ball. Like we started, this ball is going in a projectile motion of v of naught. I'm just going to call it v, which is a resultant of v in the x-axis and v in the y-axis, where your angle theta is 40 degrees, and the initial speed of the ball is 22 meters per second. So your initial speed, which is this little fellow over here, is 22 meters per second. Find the maximum height that the ball goes on. Well, in order to find the maximum height, we need to find your vertical in the y direction, the x direction. So what we're looking for the height that the ball went, which is going to be your y. So basically, just to clarify it, here's the person kicking the ball. The ball is going to go in a projectile parabola going in there, and that's going to be your maximum height from over here, from the ground to the top. All right. Well, first of all, what we need to do, we need to find the acceleration, the velocity in the x and the y direction. Now, in order to find the velocity in the x and y direction, that means we need to find, so the velocity in the y direction is going to equal, and let's say, let's label this as initial velocity. That way we can actually deal with the final velocity. So the velocity, initial velocity in the y direction is going to equal your initial velocity, hypotenuse, times sine theta, which is going to be your 22 meters per second times sine 40 degrees. Same thing, your velocity in the x direction is going to equal v naught cosine theta, which is going to equal to 22 meters per second times cosine 40. Calculating the first one. I got 40 meters per second. Calculating the second one. I got 17 meters per second. So basically, the only information we don't have over here is the time that it took. So looking at our equations, again, equations, that means anything with time we can eliminate. We can eliminate this one, this one, this one. So that means we're going to be using this equation right over here. So using the equation, v final of y squared is going to equal v initial y squared plus 2a times y. Calculating for the y, that means it's going to be your final velocity in the y direction minus initial velocity in the y direction divided by 2 times a of y. That means that your y is going to equal to, now we said the v, the final velocity of the package, again, this is the initial velocity coming in. That means your final velocity is going to equal to 0. So, yeah, hold on. Your v of y, your final velocity is going to equal to 0. That means your y is going to equal 0 minus 14 meters per second squared divided by 2 times 9 is 9.8 meters per second squared. Plugging that in, what you get? 14 squared divided 2 times 9.8, which is 18.9, 18.6. 19.6, sorry. And what you get is almost 10 meters. Let's check our answer. Yep, so we got 10 meters for the distance that the maximum height that the ball went on. Now, let's say you added another question: what is the time of flight between the kickoff and the landing? So we need the time. Using the equation, we can actually go ahead and use any of the equations. So we're going to use the same equation. So the question was, what is the time of flight? Like what flight that I have? You write this down. So right now we're looking for your time, which is your t. Using the same equation that we used before, which is your y is going to equal your v naught y times t plus 1/2 expression y times t squared. Now, when the ball lands on over here, final landing, that means your y is going to equal 0 because your maximum height over here will be 0, which is your maximum height. So when it lands, this thing is going to go to 0. So that means your 0 is going to equal to your v naught y, which is going to be 2 times your 14 times t plus 1/2 times 9.8 meters per second squared times t squared, which means this is going to equal to t. If we divide all of them by t, what you're going to get? You get 0 equals 14 plus 9.8 minus divided by 2 times t. That means your t, your time is going to equal to 14 times 2 upon 9.8, and you should get 2.9 seconds. Awesome. Let's check our answer. All right, we are perfect. Now here we have another question. Calculate the range of the projectile, the range that the distance that it went to. So we kicked the ball and it went into a total distance. Let me get the little orange over here. So here's the final position. That means you want the distance, this whole distance that the ball went to, distance range, which is your x distance. In this case, we can use the same equation using the x value, your horizontal value, which is going to be your initial xt plus 1/2 ax times t. And again, because a of x, actually, let me get a different color on this. This is going to go to 0 because a of x is going to equal to 0. That means it's going to equal to v naught of t, which makes sense because your velocity is your distance over your time anyway. So, which means that your distance x is going to equal to 17 which what we got. So this is going to be v naught in the x direction, which we actually calculate v naught in the x direction at 17 meters per second. So this is going to be 17 times the time that we had, which is your 2.9 seconds. So you should get 49 meters. And that should conclude chapter 3 for Cutnell book, Motion in 2 Dimensions. If you have any questions, please email me or at mabunae@sanchez.edu or abunaemeh@gmail.com, or you can give me a call at 256-348-1480. Thank you so much for watching. Have a nice day.